Welcome to this demonstration of fitting a latent growth curve model using MPlus. And in this demonstration, we're going to focus just on linear growth. In another demonstration, we'll look at testing a quadratic effect as well. And for this example, what we're going to look at is marital quality, the wife's marital quality over 7 waves of data collection. This is 7 years of data that we have. And we start here, marital quality at wave 1, 2, 3, 4, 5, 6, and up to 7. Now, MPlus probably has the simplest way of fitting a latent variable growth curve model of any statistical package that I know of. And all it is it's got some built-in recognized commands for this. So what I'm first going to do is I'm going to specify 2 latent variables. And I'm going to call them int and SLP for intercept and slope. And then what I do is I put a bar here. Now this bar is right above the enter key, so I hit shift and then that key that gives me that bar. And then after that, I'm going to specify the variables that are indicative of growth, that I think are indicative of growth, that I want to test that for. So I'm going to copy those, put them down here. Now, if our lines are too long, MPlus will chop off the last characters and it won't read them. So I'm going to go ahead and enter this down one because that line might get a little bit long. And so now all we do is we specify the values that we would typically specify on the slope latent variable. And we want linear slope here, so we're interested in the 0, 1, 2, 3 specification. So we're going to have this at 0, this one at 1, at 2, at 3, at 4, at 5, and at 6. And I'm done. That's all you have to do to create a latent variable growth curve in Stata. Stata just knows that, all right, the 2 latent variable names that I give before this bar are going to be, the first one's going to be the intercept, and the second one's going to be the slope. I could really name those anything, but no matter what they would be named, MPlus would recognize that as the intercept and the slope of this growth curve. If I added what we'll see later in the quadratic, if I added another name here, it would assume that that is the quadratic growth. So let's go ahead and we'll run this. Save the changes. And we have our warnings here that none of them are surprising at all, 8 characters, and that some of the cases have no data at all, and so those are thrown out. Whereas if they had any data at all, they would be included in our model based on the full information maximum likelihood that MPlus uses. So the first thing we can look at here is whether or not this model that we created actually fits the data. We specified a model here. We had a hypothesis about how these 7 variables were related to one another. And the question is, well, does our data actually fit that hypothesized model? Now, a test of absolute fit is the chi-square test of model fit. And if that's significant, it means that our data significantly vary from the model, which means that the model doesn't fit. Now, because the chi-square test is influenced by sample size, it's not really a very good test of model fit. In fact, we almost always expect the p-value to be significant here. So we don't put too much stock in our chi-square test of model fit. What we're more interested in is in our relative model fit indices, like the RMSEA and the CFI TLI. And here our RMSEA, the estimate is 0.072. Now that's a little higher than we'd like it. We'd like it to be below 0.06, but it's below 0.08, so this fits moderately well. The RMSEA doesn't say that it fits really well, but it also doesn't say that it fits terribly. Now our CFI here, we'd like to see that above 0.95, and in fact it is above that. So the CFI indicates that this is a pretty good fitting model. And so based on this information, you'd probably conclude that it fits well enough. Now, it may be that there's some linear growth, some nonlinear growth going on here, quadratic, and adding a quadratic slope may increase the model fit. But that will leave for another demonstration. So let's go down here and we'll look at what MPlus has done for us. Here we have our int, or our intercept latent variable, and as they should be, all of those regression weights are constrained to 1. Those loadings are all 1. And as should be with the slope, and we specified all these, We have 0, 1, 2, 3, 4, 5, and 6. Now we have here, it again automatically putting for us a correlation between the slope and the intercept. The hypothesis being that if you start higher, you might not increase as much than if you start lower, or whatever hypothesis might be there. But in fact, we see here that the covariance between these two is significant. Therefore, the more, well, they're just significantly related. The higher the values of the intercept, the lower the values of the slope will be. And you might have some hypotheses on why that is. Now here we get to what's really pretty interesting, and that's the means of the intercept and the slope. Now again, the intercept is the value when the slope is 0. So you can see here our slope is 0 at marital quality 1. And therefore, this mean represents the average marital quality at wave 1, which is 5.05. And that's significantly different from 0, as we can see here. Now our slope is negative 0.052, which means that on average, people decrease, wives decrease in their marital quality by a factor of 0.052 over time. Now, the follow-up question is that a significant decline? And if you look at the p-value, you conclude that yes, it is in fact a significant decline. So wives on average significantly decline over time. And I emphasize the on average because of course some wives will probably increase in marital quality over time. Some wives may stay completely steady in their marital quality over time, and other wives may decrease far substantially more than 0.05 over time. The question is that variation significant? Is there significant variation in that slope? Variation that we might be able to predict why wives might differ in their rate of change over time. Well, we come down here to the variances of the intercepted slope, and we can see that the variance of the slope is 0.021, and that is significant. So the answer to the question of whether or not they significantly differ in their slopes is yes. And we could then go ahead and start predicting why some wives might decrease more or less than other wives. We can also see that the variance of the intercept is significant, meaning we can also predict the degree to which, sorry for the phone call there, the degree to which people differ in that their starting values. And that's pretty much it for M+ and latent growth curve modeling in terms of the estimation. Now we also want to maybe look at this, and M+ has a plotting command to be able to see what our growth curve looks like. So here's how you're going to plot your growth curve. What you're going to do is you're going to use the plot command, colon, and then you're going to call for the plot type 3. So you're going to say type is or equals plot 3. That'll give you the options you want. And you want series equals, and then simply these variables. Now, something that I learned with this that was actually a bit frustrating, but now that I know it, I can pass this little wisdom on to you. If these are more than 8 characters long, and so if the variables are more than 8 characters long, we know that M+ chops those off. And so in the series here, if it is more than 8 characters, it's only going to take the first few, and then after that, it's just going to think that they're all the same variable. So what we need to do is we need to rename these. All I'm going to do is I'm just going to eliminate the QAL from all of these so that we have shorter variable names. And that will actually make this work correctly. So if it doesn't look like your plot is working as it should, what you ought to do is first see if your variables are over 8 characters long. So here we go. I have now reduced them to under 8 characters. And the series, I'm just going to say, is marital quality at wave 1 through marital quality at wave 6. And then all I need to do is I need to put a star there. And what the star does is it simply assumes that For the x values, it's 0, 1, 2, 3, 4, 5, 6. That's the default. Oh, I'm sorry. There's the star. It simply assumes 0, 1, 2, 3, 4, 5, 6, which is typical. If for some reason these were different, if you had different values up here, you want to put SLP, or the value of your slope that would be included in there. But for our purposes, because 0, 1, 2, 3, 4 SLP here or a star, it would be the exact same values. So we can just put a star there. So now let's go ahead and run this. We'll first save it, then run it, and now you can see up here we have our graphs, and we can look at our estimated means. So the estimated means at each of those 7 time points, and you can see the decline there. So starts at just above 5 and then declines to just below 5. So that's how you'd look at plots in M+. And this is going to be a little more useful to us, especially as we look at quadratic and as we get into mixture modeling. So that's the tutorial for a latent variable growth curve model using M+.